preparation for paving plants. Talk about the paver, and we're going to talk about the construction process. And again, this is a quick run through. For example, in the roadway inspection class and South Dakota pavement inspection class in North Dakota, when we start talking about pavers, we'll spend 2 or 3 hours in one session just talking about the paver. And we spend an hour just talking about paver controls, grade and slope control. But obviously we're going to breeze through this a little bit faster, but there's a lot of good sections in that hot mix asphalt paving handbook too. So as we get into the actual paving and construction process, what's kind of driving the process? Well, what's driving the process is the distress that's in the existing pavement. And typical problems, distresses that you can see, cracking, potholing, rutting or surface deformation, raveling or other surface defects are typically what drives a project to get on the bid list and in the project program and the programming list. And so hopefully the project that we're going to work with and talk about, for example, in the pavement roadway inspection class, is dealing with a project approach that's going to address these distress issues. And that's not always the case. The time lapse sometimes between the identification and notation of a pavement distress where it's gotten to be a problem and the time that job is let and constructed can be 3, 4, 5 years sometimes. But I'm going to kind of hit some high spots of what you typically see. And one of the basic problems across the Dakotas is thermal cracking, cold temperature cracking, thermal cracking, kind of like we talked about earlier when we were talking about binder and the PG binder spec. And so this particular road, and quite frankly, I can't remember if this is North Dakota or South Dakota, but as you look down the road, you can see those transverse cracks, right? And they're on about a 40 to 50 foot spacing, and pretty consistent as well. And as you look at that, those become an issue. The crack itself doesn't necessarily create the issue. What happens after the crack is there is what causes the issue. And obviously cracks, they expand and contract with the seasons, expand in the summer, contract in the winter. And so when you really notice them is this time of year. Although we haven't been that cold yet this time of year, at least in the Pierre area. But as they contract, obviously they're wide open. And what also happens this time of year, snow and ice. So you get incompressibles into those. In the spring, when everything starts thawing, you got an avenue for the moisture to work both ways. And I don't care whether it's rigid pavement, whether it's flexible pavement, moisture is the big enemy of pavements. I mean, after 40 years, that's about one of the few things I can state with affirmity. And even in Wyoming, where some places, it's 11 inches of moisture a year, it was the killer of pavements. So what ends up happening in a lot of cases with those cracks, number one, they become a maintenance issue, they become a ride issue. But from a maintenance issue, if they aren't sealed, that moisture starts working back and forth, and it'll pump the finer materials out from the base underneath, which creates a void. And now when it gets hot, and especially the traffic keeps getting heavier and heavier, and radial tires keep getting more radial, in other words, stiffer, is it starts bending in on it. And now you have what depresses maintenance foreman is called a depressed thermal crack. And now it's a huge issue, both from a ride standpoint, and it collects more moisture, and it catches plow blades when it comes off the leaf side. And the repairs are, from a maintenance standpoint and construction standpoint, are very, very expensive. And so that's one of the main issues. And I wanted to note, because this particular picture, I threw it in there for a reason, is you can see where we've retrofitted rumble strips down the center line for safety purposes, that center line stripe. That's also a joint line, right? When we paved this road or put an overlay on it, it was open to traffic, so you're paving one lane at a time. So you got a longitudinal cold joint, what's called a longitudinal cold joint, down the center of that road. It's essentially the the connection between the two different construction processes. And now that we put rumble strips in those, they expose, it's tougher to get density. It's tougher to place that mix when it's an unconfined edge on the first pass and when it's a matching edge on the second pass or the joining pass. And so density is a big issue in states like North Dakota and South Dakota. North Dakota's gone to essentially all projects last year had a joint density spec, a longitudinal joint density spec. And that's one of the reasons why, because that crack too, it's not going to move as much, but it's just as susceptible, particularly when you have a cistern for water to set and absorb into that crack, over the course of months. So that's generally, when you're looking at a distress. And, in the old days prior to PG binder, a lot of times the binder pen grade or viscosity was what was cheapest on the market. And cheapest is not always best, as we see as we get into performance graded binders where we can compensate for that low temperature cracking. So what are the causes of that distress? Again, these are things that should be looked at early to determine what needs to be done, but improper thickness design, improper mix design. Prior to doing the QC/QA, that was one of the issues, is what looked good in the recipe, what looked good on a countertop in a lab isn't necessarily going to play well when you get into a hot plant that's running 400 ton an hour. And you're using stockpiles and not pans to feed the material out of, and you're using a cold feed belt to put them together and into a drum. Another common one is poor subgrade or base support. Number 1 and number 3 sometimes fit together real well here, but in the Dakotas, a kind of a overlying problem, particularly up and down the river, is you have moisture susceptible fine grained soils. And we already determined that they have quite a bit of shale in them. And so any place where you have moisture getting into and out of that material, it weakens it, hardens it, weakens it, hardens it. This time of year, we don't have usually any problem with base support, right? It's all frozen. But it's kind of those transition periods when the frost is going in, or wet periods in the spring and the frost is coming out, that can create that issue. And so we tend to take base support and subgrade support as a single point in time, but it's not. It's very seasonal. And it's not only seasonal from spring, summer, fall, winter, but from year to year. I mean, this year compared to last year, winter-wise, I'll take this year every day and Sunday, right? But the other thing, the fourth one, is definitely in play. The traffic was higher than expected. I can tell you the average age of those asphalt pavements approaching 40 years. None of them were designed for a 40-year life. Grain hauls were a lot more limited. They were done on 2-axle, 4-ton trucks. Now you go by a farm and, if it's a big enough farming operation, they got a fleet of tractors and semi-trailers to haul grain any time of year when the market's right in any direction. And they haul load upon load upon load. The last 2 items, lack of maintenance. I came out when we moved back to South Dakota as a district maintenance engineer, and it always killed me. I just shake my head. I was talking to a guy a couple of weeks ago about this as well, a county road supervisor. Is what would you do on maintenance on the system when you had a hard winter? The worst winter you could have, a lot of snow and ice control, a lot of periods of floor ice, heavy snow in the borrow ditches. Well, guess what happens? Your snow and ice control budget goes over budget. So what's the first thing you do that next spring and summer? To save money, you cut the pavement preservation budget. So no chip seals this year. So at the time you really should be hitting it, hammering it for preventative maintenance from a budget standpoint, you can't. And so that lack of maintenance isn't meant to be detrimental to anybody or any individual. It's kind of a problem, a symptomatic problem in the way we budget. When I was in Wyoming, I always said, hey, these years where we save money on the snow and ice control instead of throwing that back, of course, that's at that time was basically 100% state funds, no federal funds involved. So can't we throw that into a holding fund so the bad winter that comes up, we know it's going to come, is we've got money in that holding fund that we can still do our chip seals and crack sealing the next year when they should be done, and couldn't make that dog hunt. So, and then time and environment, that's the whole key. Is I can feel it in my knees, pavements feel it, they're out in that exposure 24 hours a day, 7 days a week, 365 days, year after year after year. I wanted to talk a little bit again, introduction course about layers, surfacing layers. Generally the type of mix and the type of construction controls are going to be dictated by the layer we're working on. I already mentioned the term wearing course. Wearing course is the typical definition of that top lift, the part where the rubber hits the road, so to speak, and that's in the surface layer. And so what are we definitely interested in? Well, friction. That's the tire interface. From a traffic safety standpoint, friction is important, and that can go into play as far as the type of aggregate we choose and the hardness of that aggregate or toughness. Smoothness. We have IRI, or surface quality ride quality specifications or tolerances in both states now. Permeability or impermeability is probably the better way to address this for a surface layer. We want it to be a true roof over our section. And then durable, again, that time and environment. It needs to be durable and stable. And more, particularly in more of the urban areas, and I know that sounds funny to say that in the Dakotas, but you get in Sioux Falls, Fargo, Bismarck, Rapid City, more and more of an issue is noise. That tire interface, you need friction, you need smoothness, and you need permeability and durability, but just don't, wake up the neighbor type thing. And then drainage, a very important one, as I mentioned, about moisture being the biggest killer of pavement service life. So then generally underneath that are intermediate layers. A lot of times those are called binder courses. You don't see too many in our states, but there are specific binder course definitions. In a lot of cases you can decrease the aggregate requirements because the load is more dispersed when it hits lower into that surfacing. And at that point, they're there to distribute loads. And then the base course. And the base course underneath the, quote, improved surfacing layers can be aggregate base course is what we typically see. You can also see, asphalt treated bases, cement treated bases, and so forth. And then I'm going to talk a little bit about leveling courses, since, in the type of work we do in the Dakotas, the leveling course is kind of that step from existing pavement to pavement preservation or pavement rehabilitation strategy. Here's a cutout, actually not far from where I'm sitting here. They just happen to be widening it. Dean probably recognizes this, but it was on the truck route, US 1483 truck route here in Pierre. They were widening, so they had to cut straight down. I happened to be hopping across this road to my office, which is in the distance there, and I dropped my car off at the Chevrolet dealer and saw this cut, and so I pulled my camera out real quick, and it's a really good visual representation of what I just talked about. Down at the very bottom there, you can kind of see the subgrade or a sub-base course, and then the base course itself, and then the asphalt surfacing layers above it. And that at this location, I mean, that truck route's been there a long time. It hasn't been 5 lanes for a long time, but this was in the older section. And a couple things to think about is each of those layers has to do its job, but the other thing it kind of points out is you can go back to plans and as constructed plans, and it says, hey, I've got 4 or 5 inches of aggregate base. Well, even in this photo, right, if you go to the left side of the photo, there's probably 6 or 7 inches of base, but there's a little bobble in there on the far right side where it's probably 4 or 5 inches. And so take that into consideration too. It's kind of like in a lot of cases, you need to look at the least common denominator from a structural standpoint. Different mixture types. Generally, obviously we use super pave, but we use dense graded mixes. They can be on the coarse side or the fine side. As I mentioned earlier, probably 98% of the mixes are fine dense graded mixes in the Dakotas. There are gap graded mixes out there. A good example is SMA, stone mastic or stone matrix asphalt. We're going to look at some pictures, talk about that a little bit. And then down south where you get to, high rainfall areas and non-freeze, you see a lot of open graded friction courses that are designed to funnel the water away from the surface, the interface of the tire and the pavement, to avoid or to limit the amount of hydroplaning and accidents that occur. So with dense graded mixes, what are we looking at? Essentially an even distribution of the particle sizes, aggregate particle sizes. So on that little picture on the right, you can kind of see that is, you got the smaller, the minus number 8 mineral filler. You got the dust, the 200, you can't even see that, but you got the intermediate, kind of the sand fraction, the plus number 30 sieve, and then the plus 4 coarse aggregate, and it's not all 1 inch. It's a distribution between 3/8 inch, quarter inch, 3/8 inch, half inch, and so forth. And that's what we're looking at. And that's the majority of our mixes in the Dakotas. SMA, I got a few shots here, and we're seeing more and more of this. Again, stone mastic asphalt, stone matrix asphalt. I can't remember which one of those is patented, and you're supposed to use the opposite, so hopefully I guessed right. In South Dakota, the specification term is a Class S asphalt mixture. And this is a core from an existing roadway there in the picture. And you can kind of see it. It's gap graded. It's highly, a lot of coarse aggregate and a big gap between that and the filler material, mineral filler and sand. And in fact, in a lot of cases, fly ash is added as a mineral filler as well. And then some type of cellulose fibers added as well, because they are high VMA, voids and mineral aggregate mixes. They're designed to be that way. And therefore, they'll typically be higher in asphalt content, which is great from a durability standpoint. This happens to be, this particular SMA is south of Sioux Falls on I-29 in South Dakota. It was just redone here. I think last year, year before, was 18 years old. The SMA, no chip seals, on top of a super pave overlay, on top of long jointed concrete pavement, basically. And the thing about it is, particularly when it first goes down, it's high in oil content. Almost looks, you see that, particularly in that passing lane, you kind of see those lighter lines. When I see that, sometimes I worry about rutting. Well, SMAs are very rut resistant. And I've got pictures of testing that's been done both in South Dakota and North Dakota under loaded wheel testing. And I mean, that stuff you can hammer and hammer and hammer, and it's not going to rut. This is Interstate 29 in North Dakota. In fact, in the background there, you can see the casino. So this is just north of the state line. I included this for a couple reasons. Number one, it's a better close-up shot. When you first look at it, it looks like it's textured and it's going to be porous. But when you get it up to 95%, essentially at some point it refuses to come together, and that's the point that you want to hit, is it's impermeable, but it has a very porous or open graded surface, which helps get the water and snow and ice off of it. It also helps hold the liquid de-icing and anti-icing agents. And it's very tough and resilient, even in a thin lift like this. So, again, this is on North Dakota on I-29, but I also included this is in the middle of that picture. You see a reason why that roller should never come off of a hot mat. If everybody picked that up right away, is the roller for some reason here ducked off. Well, they should have done it back in the cold section, because you ain't going to roll that out, and that's going to be tough matching that joint. And we'll get into that a little bit later, and we talk about those things in inspection class quite a bit. Here's some cores out of that job on I-29 in North Dakota. And again, that's 4 or 5 years ago. I can't remember. You'll notice the kind of the asphalt on that left core. Why do you suppose that is? Asphalt rich, when you put the core bit and try doing your core, especially if it isn't a clean new core bit, creates heat, and the heat draws that thermoplastic asphalt material out and ends up coating the core. But you can see from the one on the right as well, the aggregate structure. really it's kind of a stone on stone concept with a lot of asphalt in it for durability, and you get stone on stone, you get high quality aggregates, you get the higher asphalt content. And the PG grade, since it's at the surface or very surface of the road, is generally your most aggressive PG binder grade, like a 64 minus 34. In South Dakota, it'd probably be a PG 58H or V minus 34 in North Dakota now, from what we talked about this morning. Okay, so most of these things on preparation for paving have already been dictated on the project through the project development process, but I wanted to talk a little bit about some of these. If this thing clicks forth. And I'm just going to talk about probably the more familiar preparation for most of the projects we do, and of course first and foremost is asphalt overlays. Overlays, the primary purpose is, number one, we want to improve ride quality. Over time, either due to subgrade support or lack of density in portions of the original pavement, or whatever the reason, you get these surface irregularities. And we're kind of looking at a cross section, the line being the existing pavement exaggerated in the overlay that we're doing on top of it. In addition, as we do that, we talked about pavement thickness, we're adding structural capacity to the roadway. So that road that was designed probably and missed the mark by 40% on the traffic loadings 20 years ago, we're going to try and catch up with it by adding some additional structural capacity and look forward for the next 20 years and probably miss that traffic count by 50% as well. But the extent of preparation needed is really a function of the existing surface. What's the distress? And just some cardinal rules, I guess, particularly in overlay applications, is any failed areas need to be removed and replaced. I mean, you can leave them there and you can make it look flat, black, and beautiful, but that cyst is still down there, that cancer is still down there, and it's going to come back under loading and under environment and under time. You need to patch potholes, clean and fill cracks. In this case, your overlay program's got to match what your maintenance program is. You want to hit the timing right so that a lot of these maintenance functions have been done and completed maybe the year or 2 years before the overlay's coming in. If you do that, you're going to optimize the performance of the overlay. And if you have any rutting, again, older pavements, old Marshall mixes done prior to QCQA, wasn't unusual to have some rutting or wheel path deformation. And if that's the case, you need to address that, or else you're going to have differential compaction and issues result from that as well. A lot of times now we do more milling, so we get rid of the ruts that way. If you're not doing any milling, there's rut box technique or blade leveling technique. If you're trying to bridge poor quality areas or weak areas, it's not wise. That's why you need to remove them. When you remove them, you want to get back to sound pavement. And we talk about tack coat and in the inspection class quite a bit, but it applies to patches as well. Is you need to tack not just the bottom surfaces layer to layer, but the edges, the vertical faces as well. And if you have to do a full dig out, you got to work your way back up. And remember, when you're working your way back up, now you're using differential materials. You're probably not matching that original material that was underneath that roadway, so you kind of have to take that into play. And if it was moisture or drainage that caused the problem, it doesn't do any good to just do the repair and not expect the problem not to come back. So kind of got to keep your eye open, not just where the distress is, but where it's coming from. And when you build it back, build in lifts, and with compaction. Tack coat, as I mentioned, is just trying to get a bond, a weld between the existing surface and the overlay. If you don't have that, I worked on a job just this last summer that was in a city. I'm not going to name the city or the contractor, but for lack of some tack, the slippage occurred, and now you had a boiling pavement with some smile breaks in it, smiley slippage distress, and guess what? That's a brand new pavement, and it ain't going to get better with age. And for literally pennies on the square yard for tack, you just ruin, dollars and dollars, probably hundreds of dollars per square yard of pavement. Again, the cardinal rules is you want the surface to be clean. More and more with traffic, as I mentioned, coming in and out of fields and all occurring is, emulsion. The emulsified asphalts we typically use for tack coat, right? The CSS1, CSS1, CSS1H, SS1H. By definition, they have 40% water. What happens when you put water on a dirty surface? The dirt becomes mud. So now you're doing the opposite of tacking those surfaces. You're putting a slip plane in between them. So, and then don't forget, particularly in urban construction, is the faces of curb and gutter, cold joints as well. In North Dakota, that's required. In South Dakota as well, I believe, is when you tack for the next layer, you are required to tack the vertical face of the adjacent laydown path, and in fact overlap it. So in North Dakota, it actually says you got to double the application rate for those vertical faces. And coming into structures or approach slabs as well. Generally, you want to apply it to a warm surface. Somebody asked about that. How long does it take to break? Well, the warmer it is out, the quicker it's going to break. And you want to make sure you don't start that overlay process until that tack. And again, break means the water comes out of the emulsion. If you don't, you're going to trap that water in that bond layer. What happens when water hits mix that's coming down at 280 or 290 degrees? Turns into steam. The steam wants to get out, and so it's going to open the porosity of the mix, make it really difficult to compact as well. This is that dilution thing I talked about. Typically we're using those products, emulsion products, for tack. A lot of times they'll dilute it so that you can get a higher rate through the distributor truck and the nozzles, the snivvies, and make sure they get a uniform application. If you double up by diluting it 1-to-1 with water, you got to double the shot rate, because what we're really looking for is a residual asphalt amount on the road. And typically, depending on the road, that's going to be somewhere. This is residual asphalt now, not emulsion. Residual asphalt of 0.02 to 0.05 gallons per square yard. Well, we know that by specification, that emulsion is 40% water. So that's really saying on the plan sheet, you're going to see something like 0.04, 0.05 to 0.08 gallons per square yard. And by definition, that's undiluted emulsion. So if we start diluting it in the field, you got to increase that shot rate with reciprocity. We'll do those calculations in inspection class if you come through that. Too much versus too little. By far, in my experience, I've seen a lot more of the right and very few problems with the left. So too little in many, many cases. In fact, as I mentioned this year, where it caused a problem in a removal. Too much, it could literally happen, but generally that kind of works against our system. Nobody wants to put too much down because they're eating the cost. But if you get too much down, it could cause a problem. But generally, the problems I've seen lean to the too little. So when you get to overlays on rigid slabs or using fractured slab technology, this is actually up on I-94 in North Dakota, west of Jamestown, and this was in the eastbound lane. This was an old plain jointed concrete pavement retrofitted with load transfer bars, I think, but was getting to be pretty ride intolerant. Were some other issues. Otherwise in fairly sound shape. In this case, the prep included, you can see in front of you, is what's called a guillotine hammer. It's a double hammer, just drop weight. What you're trying to do is break that slab up from 12 or 14 feet into shorter length slabs so they don't move thermally in 12-foot patterns. South Dakota's done this in a number of locations, typically using the multi-head drop hammer. And I've seen jobs that use a resonant hammer, which is kind of a vibrating head down, but whatever works based on the thickness and type of concrete and what's underneath it. But what I wanted to get to was, in this case, they did a straight asphalt overlay on it. And so you have to be careful on the tack, right? If that concrete is polished, the aggregate's polished and smooth, you definitely want to get the section welded and with the tack. And if you don't hit the tack well here, this wasn't too polished, and you can see it kind of had the longitudinal tining in it, so it was able to catch and therefore bond together and easier to get density in the wearing course. Wanted to bring this project up. It's kind of an ongoing process for the last 3 years, working with the city of Sioux Falls and contractors, producers down in that area. This is 41st Street. If you're familiar with the area, this was last year, well, 2019 job. There's also a job on the east end of this in 2020, a little different approach. Concrete in really poor condition. Believe me, it's done yeoman's duty though. One of the busiest roads in the state of South Dakota. But you can see there's multi-generation impact from widening this section, this urban section, and also different generational ages or of patching material. I mean, it was a real zoo for prepping it. But the better you do the prep, the better performance you're going to get. And in this case, it was a thin lift overlay going down. And I thought this picture was a good one in a couple ways. Is number one, the thin lift mix. In this case, instead of the 12.5 millimeter, it actually fell between a 6.5 millimeter and a 9.5 millimeter, so roughly a 3/8 inch minus super pave mix. In this case, they ran a leveling course of 3/4 inches with the paver after they'd done the prep and repair, and then did the overlay, which I think was 1 1/8 with this reduced nominal maximum aggregate size mix. And in this case, it was a all virgin mix, obviously with quartzite in the Sioux Falls area. If I remember right, we put a spec on it for PG plus, but it was a 70 minus 34 roughly from that PG binder terminology we talked about this morning. So highly modified asphalt. One of the things with smaller particle size mixes is it takes more asphalt because you got more surface area to coat. So it is a little higher asphalt content. I think this was around 6.3, which for a typical 12.5 millimeter all virgin quartzite mix in that area of the state, you're probably looking at 5.5, 5.6. And volumetrically and from a performance standpoint, worked well. It was done under traffic. But I just, particularly for city and county people that are maybe sitting in here, is, for both states, North Dakota and South Dakota, it's kind of one size fits all, the 12.5 millimeter nominal maximum aggregate size mix. There's a whole plethora of super pave mixes down the 9.5 millimeter. Some states even use 4.75 millimeter super pave mixes for thin lifts. And then you get a lot better construction. It might be counterintuitive, but if you're going to do a thin lift and you're going to utilize your compaction process with all the tools in the tool shed, you got to have roughly a 3-to-1 ratio between the nominal maximum aggregate size and your lift thickness, and preferably 4-to-1. So this has been down for a couple years now. This is what it looked like after striping, and roughly I call it a short mile. It's kind of a short section line near the section or the county line, and 5 lanes wide with right turn lanes as well in places, as you can see. So something else to consider. The next kind of routine thing we see more and more now is cold milling or rotomilling as a preparation method. A couple interesting things about that is, number one, this generates a lot of the resin that we recycle right back into the mixture, and it comes from the mill tailings or the milling process. You still hear it, and I think in that black book, the Hot Mix Asphalt Handbook, they call it cold planing. Same thing. Nice part about milling is the mill works off grade and slope control just like the paver does, but it does it in opposite directions. A paver, and we'll get into that in a while here, but basically a self-leveling free-floating screed on a paver fills the low spots and skims the high spots. That's how you get smoothness and uniformity. And they do that utilizing grade and slope control on the paver. The milling machine uses the same grade and slope control, but the opposite direction. Mills the high spots and skips the low spots. And so right out front, if you're going to use milling, you want to get the first advantage of it is it's your first opportunity to get smoothness. And a lot of times this can take the place of a leveling course because it's going to do the leveling with grade and slope control. The other thing is most pavement distresses concentrate in the top inch or two of the mat because they're most exposed to thermal movement, they're most exposed to moisture, they're most exposed to traffic loading, high tire distribution in that top 2 inches. So that's where the distresses occur. So if you mill out, if you have 2 inches that's distressed and you mill out 2 inches, you're probably down to pretty good pavement, and now I can start over. I can do a mill and fill, which is essentially just replacing the 2 inches I milled out, or I can do a mill and overlay. Maybe I mill out 2 inches and put, two 2-inch lifts on top, a mill and overlay. So, and the milling machines are better and better as far as control. The cutting heads are much better, especially from when I started, and they're more productive. Number one, they don't break down every 15 minutes like they used to 30 years ago, but they can go to extended widths, which is pretty important in our world when you're dealing with 2-lane. Is, if you can shorten the number of passes, you shorten the construction job, you get the wrap in the yard, working on getting it ready for the plant and the production. It's got grade and slope controls, and in addition, there's a lot of milling. You can ride on that for, depending on the existing section, you can ride on that for extended length of time. You have to be careful if the section's too thin and the milling head's doing its job, it might be cutting down to, places I've seen places where it was supposed to mill 1.5 inches and the plan showed a 4-inch mat, and when the mill came through, it was kicking out the base course in places. So that's kind of an idea on the distress that was created to cause that project to begin with. But the surface texture is great. In some cases almost too good, particularly in South Dakota if it's around the rally time where you have to put the signs up for motorcycles to be careful on a milled surface. Both states, North Dakota and South Dakota, have actually done kind of a subset of this as well called micro milling, where those teeth on the milling head are a lot closer together and you're not milling as deep. And in some cases, it's a pavement preservation tool in and of itself, standalone. What you're doing is putting friction back into the roadway, and in a lot of cases, it'll kick some profile benefits out of it. But in a lot of cases, these are areas that are been identified as high accident areas because of skidding, like on turns, hills, curves, and bridges, right? From a maintenance standpoint. And then they come back with a polymer type, high friction wear chip seal in those areas. So, but I know some states actually use the micro milling in stage, and they'll do the micro milling maybe a year or two ahead. And obviously you got to broom it and restripe it, but it's a standalone process as well. And there's a picture, and I can't remember again which state this is in. Kind of just noticed it now. It does trim out my comment about traffic coming in and off the side roads. If you look in the background of that picture, you can see, I don't know if that's a harvest rig or a grain truck coming off that field approach. But you can see the milling texture. Depth is extremely important, both for your takeoff on materials if you're using it for wrap. But you can also see this was a pavement, obviously part of the milling is because it had thermal cracking. As you look down the roadway there in the picture, you can see those transverse cracks. And you got to be careful if you don't get deep enough, that surface damage from around that transverse thermal crack, spalling, raveling, and so forth is going to chunk out. And so when you're dealing with this, depth is a key issue. You want obviously crown and slope control from the milling, but it's gonna lay bare any issues in that pavement below it. And in this case, the thermal cracking, if you look at that kind of outside wheel path looking down the lane, again, I can't remember this location, but you can kind of see the ravel pothole areas down that outside wheel path at each of those transverse cracks. And so, this is an area that probably should have been milled a little bit deeper, and maybe you had to have done a thicker overlay because of that. But the thing is it won't lie. It opens up what's there, and you can't make assumptions at that point. You can see what it is. It is what it is. So this particular shot I just wanted to show you is kind of interesting, kind of tags a few things we've talked about. This happened to be, this is on US 30, kind of east of I-15, southeast of Pocatello, Idaho. Our youngest son, his family live out in Nampa, Idaho, west of Boise, and so we were headed out there. It was a year ago, last summer, I think, and coming down off of the pass here it's lava hot springs kind of in the background to the left, and they were chip sealing this, and two things hit me. Was number one, this is on the lower part of a long downward grade, but look at the size of those chips. I mean, talk about, you get down below here, in fact you can see the trees down there, that's the Portneuf River. Then of course obviously you got the mountains, so they have a lot of good high quality aggregate, particularly for chip seals. And so this was like a 12 or 15 mile section. Here it's 4 lanes wide because of the climbing lane for the pass coming up the other way. But we were near the front of the line and in the queue. By the time I turned around when we finally got going, there was, I think it was 2 miles behind us. So, but this was a chip seals. I think I looked at the trucks and where they'd sprayed looked like a CRS or CRS2P product with pretty big chips, pretty high quality chips. The other thing I wanted to bring up with chip seals is that can be prepped more. In some cases on some projects you're seeing what's called a Texas underseal, where they actually do a chip seal and then an overlay on top of it. I know South Dakota's done this in a couple places. North Dakota actually did this and has a section under evaluation. MnDOT's done quite a bit of this. One of the things about this is where if you're not doing leveling or milling, it gives you a chance to kind of get some oil on that road, particularly if it's old and oxidized. With the chip seal, you can shoot it real heavy. The chips are more temporary for traffic friction before you get it overlaid. And of course, when you tack a chip seal, you got to tack it a lot heavier to do that bottom lift or overlay lift. Just kind of summarizing this, surface prep rarely gets due consideration. A lot of times we get bit by the time lapse between when it goes into the program and when it's actually bid and constructed, and that can eat you up if you're not careful. Just the thing to remember is the problems you don't take care of today aren't going to go away. So I mentioned you can make it flat, black, and beautiful, but whatever cyst or cancer is down there is going to come back if you don't take care of it, and they're always more costly to fix the second time around. So I'm going to go into plants, pavers, and compaction, kind of the last section. What's the asphalt plant? What's the basic purpose? Produce a quality hot asphalt mixture that contains the desired proportions of asphalt and aggregate. And when you say desired proportions, we're volumetric controlling it, which is where the third A comes in, air. The basic functions of the plant are, first and foremost, it's got to dry the aggregate. And it can't do anything until it does that, because it's got to heat that aggregate then, and of course mix it with the asphalt and come out the other end with an homogeneous mixture. Basically two types of hot plants. The batch plant that you see on the left and the drum plant on the right. By far the vast majority of tonnage with the DOTs in both states is produced via drum plants. But batch plants, you still find those. They're stationary. Our drum plants are typically traveling plants and move from job to job. Batch plants are typically stationary, and you'll find them in some cities and towns. I know there's one in Jamestown, Fargo, Sioux Falls, Rapid City. Typically they're good plants. It's just that they're not really high production, and of course the overhead cost is a little higher on those because they sit there all year round. So But the basic operations are the same. We got to store and handle materials. We got to proportion the aggregate and feed it into the drum, whether it's a dryer drum or a dryer and mixing drum. Dry and heat the aggregate, collect the dust or the exhaust, and proportion and mix asphalt with the aggregate, and then store and dispense it. Again, going back to those 3 A's, so it's at the plant, we're taking care of all 3 of those. Got to store the asphalt liquid that we're going to put in the mix that day. If you're running 400 ton an hour at 6% asphalt, you're going to need 24 tons of liquid asphalt an hour. And in a 10-hour day, that's 240 tons, or roughly 11 tanker trucks of asphalt that's got to be moving into the plant. And then, of course, the aggregate part. When we get to the aggregate issues, typically you can kind of put them into these 3 areas: segregation, degradation, and contamination. That's way too many nations, but I made it through it. Segregation, we specifically stockpile materials in certain sizes and proportions so we can do an accurate recombination at the hot plant. But what I'm talking about segregation here is in the stockpile itself. If you have a -4 pile, for example, that's got a lot of plus size or oversized material in it, it's a bad thing. And fines piles, I can't remember if I included the pictures in this intro class, but in the aggregate testing class we talk about this. The other thing is degradation. How did we build those? Every time we handle that aggregate, it's going to degrade. And if we're crushing and screening it and stockpiling it and then dry hauling it to a plant site 80, 100 miles away and restockpiling it, and then using a front end loader to feed the cold feed bins when the plant starts production, and then it finally gets to a drum where it's going to tumble through and with 300 tons of its closest, or 400 tons of its closest friends, it's going to degrade. And then contamination. And really, most contamination in our world, even with traveling plants, is water, is moisture. So here's some segregation. You look at the pile in the background there. I call these rollers. So you probably, I don't know if this is a combo rock pile, 3/8 inch minus off the crusher, but you can definitely see the finer materials kind of work to the bottom, and you got some bigger material that gravity's working down that face. And front end loader is going to come in and take out of that pile to put in the cold feed bin. And if it doesn't remix that material, it's going to be segregated from what we think is in that stockpile. This picture is actually from that black book, that hot mix asphalt paving book, but it's kind of nice because it shows kind of a couple things happening at the same time. Right hand side, I call it cross pollination. When you don't have enough space at your plant, which happens all the time for some reason, I don't understand. But anyway, you can get contamination from one pile into the next. And now you kind of have magic aggregate in between those 2 piles. Depending on how you build that stockpile in the middle of the picture, you can see here's a dump and doze type stockpile build. Well, if you got a very heavy dozer on top of that building and dumping, every time those ribs on that track hit that material, it's going to degrade it. On the asphalt side at the plant, we've got looking at storage and handling. Obviously, it's a thermoplastic material, so the storage tanks have to be heated, and they need to be large enough to minimize disruption. As I mentioned, at 400 ton an hour, that's 24 tons of liquid an hour. That can run through that's why on a lot of our plants now, you'll see 2, 3, sometimes 4 hot oil storage tanks, because you got one being loaded by the trucks coming in, one being used by the plant, and 2 in between waiting their turn. One thing, PMA in this case stands for polymer modified asphalt. Remember that rule of 90? If you add the absolute value of those 2 numbers, the high temp, low temp, and it's 98, 96, or 98 or 92 in that age, it's probably modified. Is those modifiers, if they're left in the tank for very long, will settle. I always kind of warn people that in the spring, if they've got material that they had last year and when they shut down and are setting up to run this year, you really need to recirc those tanks, because it'll striate, it'll separate with time. And if you got multiple grades on the job, different PG grades, obviously you need, and you're running the plant at different mix settings, you're going to need multiple tanks for the different PG grades. Then you have to have sampling valves, and we have to have calibrated tanks because our cutoff, we pay for asphalt separately in both North Dakota and South Dakota, and we're going to use cutoffs to determine both asphalt usage for volumetric purposes, but it's also a pay item. Permanent plants are at the top there. You'll see this now. They're bermed in from a MPDES standpoint, and you can see there's multiple tanks for multiple different products, so that plant can switch back and forth between commercial mix and highway mix, whatever. And that vertical tank, I can almost guarantee you the vertical tank in the left corner of that tank setup is the polymer modified. And it's got, number one, that's less surface area per volume, and that's got mixing sticks in it as well. But what we typically see is what's in the lower picture with the traveling drum plants is these portable plant storage tanks that can be hauled and set up. If you learn one thing out of this and you're out at the plant working is we take samples of that asphalt. It's part of the certification acceptance process. Each plant's different, has a different sampling manifold. Is let the ground person at the plant do it, and remember that's a hot, sticky, viscous, dangerous fluid. If you do happen to get sprayed, line breaks or something like that, your first indication usually is to rub it off. Actually, the first reaction is to cool it off. If you have a shower close, eye shower close, is get it cooled down, because then it'll turn into that solid phase. And actually, back in the Roman era, they actually used asphalt for bandages because they are anaerobic. They cut off air to it, and then once it's cooled off in place, you leave it there until you can get to a medical hospital or quick med outfit to do the removal and take care of the burns. By the way, there is a good resource it's on the Asphalt Institute site, and it's free, about handling asphalt and asphalt safety procedures. So we have some producers, or it's probably not a bad thing to use as a toolbox talk for safety talks for agencies and consultants, as well as you can go to that site and download those safety documents and use them for a toolbox talk. So I mentioned drum plants are by far the predominant method. In this particular one, you can kind of see the button shack on the right. You see the cold feed belt in the foreground here, coming off the cold feed bins that are kind of on the far left side off of the photo. This is a parallel flow plant. The burner's on the right side of that drum. The cold feed aggregate's coming in on the right side of that drum. The aggregate's drying and heating as it moves from right to left down that drum. In the middle of it, you can kind of see that silver thing. That's the wrap collar, where if it's a wrap job, you're putting the wrap in. You want to heat the wrap convectively, since it's a black rock. It has hydrocarbon on it, the asphalt from the wrap. And so you convectively heat it with the hot superheated or a dry superheated aggregate, and obviously the exhaust gas coming down through the drum. And then that's normally about the point where the asphalt's injected as well. And then off the left side is the discharge dam, in this case going up to a surge silo in the background of the picture. Then on the far left is the exhaust panel for the bag house fines, and we can't see the bag house, but it's down below behind that storage. So here's a close-up of the drum plant. This happens to be, again, a parallel flow plant. There's the cold feed, and you can also see the burner apparatuses there, and they're both at the same end. So this is a parallel flow versus a counterflow. Most of the plants I've seen in the Dakotas are a parallel flow. Then there's our wrap entry point. In a lot of cases with these big high production traveling plants, they were retrofitted onto the drum. Then on the left side, or the end of the discharge dam of the drum, is where our heated mixed asphalt mix comes out. Kind of an important concept is that drum's rotating, and it rotates, and it has essentially panels in it to get a veiling pattern of that aggregate. So as it first dries and then heats, that exhaust gas is streaming through kind of a continuous veil of material, the length and in 3 dimensions, I guess, down the length of that drum. Then you can see where the wrap collar is and the asphalt injection. And then the last third roughly of the drum is typically the mixing area or mixing chamber, and then out the. So here's again, most of the silos we see on our traveling plants are actually surge silos. They hold enough to kind of 80 to 100 ton to kind of keep the trucking in line and moving. And the cold feed, when we calibrate the plant, in this case, we've got what, 1, 2, 3, 4, 5. Looks like maybe one of those cold feed bins is not in use. So 4 bin splits. So 4 different aggregate materials coming in, and then we're going to calibrate it behind that wind cover there, that fairing at the bottom where the collector belt is. And that's what we're doing there. It's either a variable speed DC or an electronically controlled motor on each of those feed belts. This is the bottom of each of those feed bins. And we calibrate the plant based upon our mix design by the proportions of each of those aggregate materials that need to be between the gate opening and the speed of that collector. And then we control it from the button shack, and it's going to deliver proportioned aggregate. It's going to run over a scalping screen. You see kind of in the foreground middle there to get rid of oversized material. Batch plant, just the basic elements. You can see the drum's a lot shorter. You don't see any kind of cold feed or multiple cold feed. You're putting all the material into the drum, and the drum itself is just drying and heating the aggregate. Once it's drying and heated, it goes up that elevator on the far right of that tower that's on the left side of the photo. They call that the batch tower. And as now it's heated and dried aggregate, it's not proportioned. It's going to go over a screening deck, and typically you'll have 2, 3, 4 bins at top, which essentially are running a gradation of that material. Finer material on the left, coarser material on the right. And then each of those, as the name dictates, a batch plant, it's going to proportion by weight each of those materials out of the 4, in this case 4 separate bins, now sized for whatever our mix design is. And that's a hot bin feed percentage. And then at the very last, we add the asphalt based upon the batch size or the weight size in our mix design. And it's going to go through a pug mill. And the pug mill mixes the asphalt into the now heated, dried, and proportioned aggregate. Just a couple quick shots on mixed delivery. South Dakota requires windrow paving, and in North Dakota, the ride spec basically does as well. It's just a way to keep continual flow or movement of the paver and make up for kind of the gaps between trucks. In this case, this is a Flowboy or a Red River dump. Here, typically you see belly dumps delivering wet hauling from the plant to the paver. Again, I include the end dump here. If you're end dumping into the hopper, just a couple of cardinal sins. Never bump the paver. You always want the paver to pick up the truck. Otherwise, you're going to create bumps in the mat. And from a truck standpoint, if you're end dumping directly into the hopper, you always want to break the load before you open the tailgate, and that just means that the mass of material that's in that truck is going to slide to the back tailgate and then start discharging through the tailgate. And if you open the tailgate first and then raise the box, it's going to come out of there like a race and segregate, and actually can cause bumps as well because of the weight hitting the hopper. Paving equipment is kind of interesting. The patent for a paver has been around since the 1920s. And I mentioned this before, it's essentially a self-leveling, free-floating screed. And it's really 3 components. The tractor unit, essentially the machinery, the horsepower that runs the paver and the mix that's in the paver, the screed itself, and then the grade and slope controls. It's a lot of different colors, a lot of different flavors, but they essentially operate out of the same concept, self-leveling, free-floating screed. Here's my screed, and the only place it's connected to this tractor unit is a pin here on this arm here and one on the opposite side. So it's self-leveling, free-floating. We can raise and and lower the angle of this screed. But that can be done here. You see contacting screed here, or profile control here, and these are on tripods in this case, which you see ultrasonics or non-contacts more now, but that sends a signal here to raise or lower this lift arm here depending on the thickness. But essentially the screed's self-leveling, free floating, and if you let it do its job, it will. It's another different kind of break off of it, the tractor, the hopper, the toe. As I mentioned, the toe point here and on the opposite side is the only place where this screed is connected to this equipment. So what it's really doing is balancing forces. Obviously the speed of the paver, the P, if you want to call it that, the pull, the weight of the screed unit, which is obviously a constant, and they've gotten heavier and heavier with more and more strict ride quality specs. And then the horizontal resistance on the screed plate, so that's right here, which is where that auger is with the mix. And then the vertical resistance of the mix under the screed, which is more a function of the type of mix I'm placing and how much asphalt there is in it. But really, as long as you keep a constant speed, the only factor you have to pay attention to, and if you're going to pay attention to, is this head of material. You can think of the H, or the horizontal resistance, as the head of material in front of the screed as the paver is going down the road, and we want to keep that consistent. And basically the good rule of thumb is within plus or minus 1 or 2 inches above the shaft of that screed assembly, or that auger assembly, that's spreading that mix from the hopper back horizontally in front of us. Again, the one thing that has changed, even though the physics are the same, is just the electronic controls. Bigger horsepower, bigger screeds, but also the electronic grade and slope control. And between sensors and the electronics now, they're so much better than they used to be. They react quicker, but they're not foolproof either. So we get into that. Talk about it. So basic rule of thumb is we have to balance the mixture delivery, the paver speed, and the compaction operation, the rollers that are getting us our density. The kind of the old rules of thumb, they're in that black book. If you get into the paver, they said, well, keep paver in motion 75% of the time. Well, really, if you're going to control and get density and get good ride, if the paver's moving, that goal should be 100% of the time. I know that's not always achievable, but you ain't going to get it unless you try and achieve it. And it says keep augers turning 85% of the time. Those are the augers spreading the material horizontally in front of the screed from the tunnel chambers from the hopper back to the screed. Well, if the paver's moving, everything should be moving. Because if it isn't, there's no way you can keep a consistent head of material in front of that screed. And again, we spent a couple hours talking about this in the inspection class. And then the last piece of the puzzle is actually compaction, which is just the process of compressing a material into a smaller volume while maintaining the same mass. So we got the same weight, we're just making it smaller volume. What are we doing? Visualize the material on the table in front of you, and we're pressing down, keeping the footprint the same, but pressing down to squeeze the air out of it. And with density, we get impermeability and durability. It's essential to good performance. Typically, with the DOT, North Dakota did a couple what are called percent within limits, mainline density incentive, disincentive jobs this year. I think the upper and lower spec limit for density was 92.0 to 96.0. That's what South Dakota's used for a number of years now with the PWL spec with incentives and disincentives. And when we say density of 92.0 to 96.0, that's using the maximum theoretical density of the mix, the Rice value, so to speak, which means that you can subtract that from 100, and that's the air voids that are in that mat. And with our fine dense graded mixes, typically on our jobs, if you get the density above 92, what you're doing is eliminating the chance to have interconnected air voids. You got smaller air voids and they're not interconnected. If you think of the difference on the concrete side of things, it's the difference between entrapped air and entrained air. And it can only be achieved if the mix is confined, and it's got to be workable. You can't squeeze it out if it won't move. And that's where temperature comes into play and quality control comes into play. You know, typically we look at, you know, the compaction train or the compaction process. What most people forget, the most efficient and best portion of your compaction train is the screed itself. You know, typically it's got a tamping or vibrating unit. It's at its most uniform and it's at its hottest when it's coming through that screed. So if you got that vibrator tamping mechanism working, that's where you're going to get the best bang for the buck. And the screed's got to go over it anyway. So then you get to kind of the supplemental rolling, I'll call it, is the, you know, typically separated into phases. The first phase being the knockdown or breakdown phase, which is your first roller or set of rollers that are hitting it again when it's at its warmest, and then intermediate phase, which can be 1 or 2 rollers, and then finish is just taking any wheel marks or defects out of it. And that can be vibratory steel-wheeled rollers, it can be static steel-wheeled rollers, and number 1 and 2 can be combined in the same roller, or pneumatic or rubber-tired rollers. And now the latest technology, you've got oscillating pneumatic rollers, you know, where the wheels kind of wobble and introduce a oscillating action in, and it's just moving particles to get better density. So just some basic background, typically 10 to 14 ton rollers are normally used. If at all possible, and the thickness is there, is steel wheel vibratory is very efficient. Besides the static weight and that kind of force log you're seeing on the right side of the slide, you get the benefit of additional vibration to help move those particles and reorient them to get better density. Generally, lighter rollers are used for finish rolling. More and more, at least what I see out in the field, is whatever they're using in the breakdown phase, the knockdown roller, is they got that same roller running static as the finish roller, because if that breakdown roller breaks down, they just move the backup plan, which is that finish roller at the very back moving up to the front. Anything with the drums have to be smooth and clean. Just good practice. Otherwise, you're going to end up with defects. And with these, especially with opposite drums, is you always want the drive wheel on a steel wheel roller facing the paver for both your reversals and on near the paver and on back roll. More and more, you're kind of seeing this because of the increased emphasis and objectives with longitudinal joint density. These 3-wheel rollers are pretty hard to beat, you know, particularly if they're being used exclusively to get the longitudinal joint and don't have to do makeup passes on the main line. Pneumatic tire, again, you're getting a different type of compaction action with the pneumatic. You have offset wheels, you can change the tire pressure, and you can change the ballast, the weight of the pneumatic roller, depending on the mix and the thickness. And again, a really good way to get density. When I started, you almost always used to see pneumatic tired rollers in breakdown. But the difference there was 2 things. We didn't have a ride spec, and we didn't have polymer modified asphalt. And so you have to be careful with pneumatic tires because they'll pick up material if you're not careful, if you don't keep the tires, warm them up, heat them up, and then keep them hot. But also, if the knockdown is too great, because you're not using, for example, the vibrating screed, it can leave little marks that maybe the intermediate and finish roller don't get off. And Shay's online here, so he'll catch the drift of this. But when he comes out with that high-speed profilometer, you know, it's measuring the roughness in those wheel paths. And if one of those wheel edges happens to be coming in and out of that wheel path, the ride quality numbers are going to go down, and you're getting into penalties and maybe grinding. So just a couple shots of some different pneumatic rollers or rubber-tired rollers. Again, you can change the ballast, whole thing, and you'll see shrouds around the tires more nowadays to keep the heat in that chamber where the rubber tires are. And here's an example. I don't remember where I got this, of the pneumatic in a breakdown phase. If you look real closely, you can probably see it here. You know, these wheels are offset between front and back so that they don't follow in the same wheel track, but you can end up with these little edges here. And typically, intermediate roller, if he's getting there with steel or she on time, they'll take those out. But you know, if they miss it and you end up with an edge there, it's going to play hell both with probably your density and your ride quality. Here's a couple different vibratories, again, different shapes, brands, colors, but basically the same function. I guess the biggest thing now, and we can't get into it too far, is intelligent compaction, which is a system to deliver real-time data to those roller operators, both on pavement temperature, stiffness of the mix underneath, making sure that they're overlapping roller passes, and so forth. And those vibratory rollers, this is exaggerated, but they work off of amplitude and frequency. The center shaft there has an off-center weight that's working in the opposite direction of the drum. So it creates this up and down motion called the amplitude. And it's thousandths of an inch, not like it shows here, just to make the point. And then how fast that's occurring is the frequency. The whole idea when you're looking at a steel wheel vibratory is you want to keep the impacts per foot between 10 to 14 impacts per foot. Otherwise, you can get washboarding, obviously. If they're too close together, you're giving up efficiency and therefore roller passes, which can cost you. So you kind of have to balance this roller speed, road speed, so to speak, with whatever frequency you're set up with that vibratory roller to make sure you're maintaining that impact spacing of 10 to 14 feet. Then patterns, we'll get into that in the inspection class a lot more, but depending on the mix, location, time of year, believe me, there's 100 different variables that impact this, and we'll talk about them in the inspection. One word sums up what it takes to build a quality asphalt pavement. It's uniformity. Uniformity of the trucking, uniformity at the plant, uniformity in the stockpiles, uniformity in the haul, uniformity in the paving, uniformity in the compaction.